Okay guys, this is discussion 3.2 on functional group nomenclature. This is a little harder to do via video, so if you realize that you're not understanding it as well, make sure you come and bring lots of questions, but hopefully this will be mostly understandable. Okay, so we're going to start by talking about organic formula types. Now we've already talked about structural and condensed formulas, so you see propane's example right there, but I also want to show you how to do skeletal formulas. This isn't something that IB requires that you do, but this is certainly something that saves a lot of time and that you might want to do in college. So I'm going to show you the skeletal formula for propane. That looks like basically nothing, but the way skeletal formulas work is this. Each vertice represents a carbon atom with the correct number of hydrogens filled in. So in this skeletal structure, the end, the middle, the peak, and the other end each represent one carbon. Okay, so it's very, very simple and obviously takes almost no time to draw. Okay, so what I'm going to show you are all the rest of these. They're structural, condensed, and skeletal formulas, and we'll talk a little bit about them. Okay, so for propan 2-all, and again, we're going to talk about how to name that specifically, but that's an alcohol. You can see its condensed formula, and then you can see the the skeletal formula. On the second carbon, we draw a line and show the hydroxyl group, the OH. Okay, propanal, again, I'll teach you how to name all of these. You see the structural, condensed, and we can show the double bond just coming off the correct vertice. And where the hydrogen is, that end right there, that's not another carbon atom. That's just showing the bond to the hydrogen. Okay, and then you can see the example for propanone works similarly. And for propene, we can just show the double bond right in the skeletal structure. So it's just kind of a convenient shortcut and definitely something you'll want to know for college. I also want to talk really briefly about cyclic hydrocarbons. So these have the same general formula as alkenes, so CnH2n. So cyclobutane is C4H8, and it looks like this. So when I say cyclic, I mean they're in a ring. Okay, so there's 4 carbons in a ring, and because we don't have the carbons on the end, we have 2 fewer hydrogens. So this is an isomer of butene. So basically, you should know that these are possible structural isomers of alkene. So if you were asked to draw all the structural isomers of C5H10, you should include all isomers of pentene, which includes cyclopentane. Okay? All right, so let's talk about functional groups. These are the reactive parts of molecules. Okay? So if we replace a hydrogen with some other atom or group of atoms, it can change the properties and function of the molecule. The same functional group, for example, an OH group, which is called a hydroxyl group, can appear in many different classes of molecules. So for example, you see hydroxyl groups in alcohols, phenols, and carboxylic acids. Okay, so there's some functional groups that you need to only recognize. So you need to be able to circle them and say that that is an amino group, that's a carboxamide group, but you don't need to actually be able to name these molecules. So the way this is written, the class of molecule is amine, and then in parentheses the functional group. So if you were asked to identify the functional group and you wrote amine, it would be incorrect. It's an amino group. Okay, so an amino group has a nitrogen basically, and it can be bonded to 2 hydrogens like as is shown here, but it could also be bonded to other carbon chains. Now, anytime you see the notation R, that basically means any carbon chain. Okay, so that's one example, structural formula, and there's an example of how it might look. Okay, an amide, or the functional group name is carboxamide, looks like this. So we have any R group, then we have a carbon that's double bonded to an oxygen, then bonded to a nitrogen, and 2 other carbon chains. Okay, those R2 and R3 groups can be hydrogens or longer carbon chains, if that makes sense. The most important thing is that we have the double bonded oxygen and then a nitrogen on the same carbon. Nitrile group is the class of molecules cyano groups. Look like this. It's a carbon triple bonded to a nitrogen and bonded to any carbon chain, and there's an example. And arenes, which is called a phenyl group, looks like this. So this is a cyclic group. There's 6 carbons, and then we have alternating double bonds. Now, we'll talk more later on about resonance, but those double bonds aren't necessarily in that position. They can rotate positions. It's just alternating double bonds, and there's an example. Okay, let's talk about some of the groups that we're going to name as well. So those groups that you just saw, you just need to be able to recognize them and identify the functional group. But we're going to now learn how to name some of these other groups. So halogenoalkanes, we name these just like we named alkyl substituents in 3.1. So the prefixes are chloro, bromo, fluoro, and iodo. And we number to give the first substituent of any kind the lowest number. Okay, so here's what I want you to do. Since we've already learned basic organic nomenclature, I think you'll find that for a lot of these, just by looking at the name, you can figure out exactly what it's supposed to look like. So what I'd like you to do is pause and see if you can figure out how to draw those without me even giving you any more information. So pause and try these and then we'll go over them. Okay, so 2-chloro-3-methylhexane. So we draw a hexane chain. On the second carbon, we have a chlorine atom, and on the third, we have a methyl group. 2-iodobutane. This is condensed just because space is a little bit limited here. It's just a 4-carbon chain, and on the second carbon, we have an iodine atom. Okay, hydroxyl groups. Molecules with one hydroxyl group alone are classified as alcohols. The class name is alcohol, but the functional group is hydroxyl. So again, if you were asked to identify the functional group in a molecule, you'd want to make sure that you called it a hydroxyl group. To name these, we end the name of the alkane or the alkene with -al, and we have to put a number before the -al to indicate the placement. So in butan 1-al, the hydroxyl group would be on the first carbon. The alcohol takes precedence over alkyl like methyl and ethyl and halide substituents in numbering carbons. Okay, so I want you to try these two examples. So pause for a second, try these, and we'll go over them. Okay, so to draw the structure of butan 1-al, we have a 4-carbon chain and the OH or hydroxyl group is on the first carbon. Now I put it on the right, and oftentimes you'll see it drawn on the right even if it's the first carbon, but remember it doesn't matter because we're just going to number to give the lowest numbers possible. So if you saw this, you would still know that it was called butan 1-al. Okay, and the molecules there, you're naming them below. So propan 2-al is the first example. We see that the longest chain is 3 carbons, so it's propane. On the second carbon, we have the hydroxyl group, so it's propan 2-al. And the next example is 3-methyl-pentan 2-al. Our longest carbon chain is 5 carbons, so pentane. On the third carbon, we have a methyl group, and on the second carbon, we have a hydroxyl group. Okay? It's kind of a clunky name, but if you look at that, it makes a lot of sense, and I think that you could pretty easily draw that structure. Okay, moving right along, let's talk about carbonyl groups. So the carbonyl group is a carbon double bonded to an oxygen, and there's 2 classes of molecule that contain only a carbonyl group, aldehydes and ketones. So here's the difference. In an aldehyde, the carbonyl is at the end of the carbon chain. Doesn't matter which end, but as long as it's on the last carbon in the chain, that's what makes it an aldehyde. If it's a ketone, it's going to be somewhere in the middle. Doesn't matter where it is in the middle, but it has to be in the middle. To name an aldehyde, we end the name of the compound with the suffix -al. We don't have to number this because by definition, since it's on the end, that is the first carbon. Okay, so we're always going to start numbering at the aldehyde. For ketones, we're going to end the name of the compound with the suffix -one. We're going to give it the lowest carbon number possible, and we're going to place the number before the -one. Okay, so it's sort of similar to the way that you indicated the number with alcohol naming. Okay, so I have a couple of these done for you just so you can see. So propanal, I know I need a 3-carbon chain, and I have to put the carbonyl on one end, doesn't matter which. 5-methylhexane 2-one is what I would call this. Okay, so this is an example of a ketone because the carbonyl group is not on the end. I want to give that the lowest number possible, so I'm going to start numbering from the right. The longest chain is 6 carbons. Okay, so it's a hexane. And then on the 5th carbon, there's a methyl group. So I would call this 5-methylhexane 2-one. And then below, I showed the structure of butanal. Okay, and again, it doesn't matter which end you put the carbonyl group on for an aldehyde, it's on the end, and that's by definition the first carbon. So pause for a second, try to name the last one in the top, and draw the two structures in the bottom. Okay. So the last name on the top is 4-methyl-pentan-2-one, and again, we're giving the ketone the lower number. And then when we draw the structures on the bottom, pentan-3-one, I think it's pretty self-explanatory. And then 3-ethylhexanal. Again, you could have drawn it the opposite way. It really doesn't matter. I have the aldehyde on, or the carbonyl group for the aldehyde on the right side, and then I start numbering from there. Okay, carboxylic acids. These contain both a hydroxyl and a carbonyl group bonded to the same carbon. So altogether that has a different functional group name. We call that a carboxyl group. So when we want to name carboxylic acids, we're going to take off the final E in the name and add oic acid. So if I had butane with a carboxyl group on one end, I would take the E off of butane and call it butanoic acid. Much like aldehydes, for carboxylic acids, the functional group is always located at carbon 1 by definition, so we don't have to indicate placement. Okay, so see if you can draw these two examples, and then we'll go over it. Okay, so ethanoic acid. So we know that has to be a 2-carbon chain with a carboxyl group on one end. Okay, again, I drew it on the right. You'll usually see these on the right side. I don't know why we always do that, but people seem to do that. And then for 3-methylbutanoic acid, I know it's a 4-carbon chain with a carboxyl group on one end and a methyl group on the 3rd carbon. So again, the carboxyl group is on the right, and actually this is pentanoic acid. Sorry, guys. But you're brave. You'll be okay. Just take a carbon off the end there. Okay, for ethers, the general formula is ROR. Not actually. Okay, so it's ROR prime. So what that means is that we have a carbon chain, a bridging oxygen, and then another carbon chain. They could be the same or they could be different. You're only going to have to name straight chain ethers in this class. So it's really easy. You're going to find the shorter chain. You're going to use the right prefix for the number of carbons in that chain. Then you're going to write oxy. Then you're going to find the longer chain. This is the main chain. You're going to name it like a normal alkane. So methoxyethane looks like this. I have a 1-carbon chain, the meth part, a bridging oxygen, oxy, and a 2-carbon chain, ethane. Okay? Try to name this other ether. Okay, so when I look at this, the shorter chain is 2 carbons. So I'm going to use the prefix eth. Then I have a bridging oxygen and a 3-carbon chain. So I'm going to call this ethoxypropane. Okay, and finally, esters. So esters are formed from a condensation reaction of an alcohol and carboxylic acid. Okay, so condensation reactions are going to produce water, right? Just like the water condensing, H2O. Okay, so we're going to show you in class how condensation reactions happen. For now, you don't need to be able to show the entire reaction, but it does help to understand that that's where it comes from in order to name it. So there's going to be 2 alkyl groups, and you're going to see that one is double bonded to an oxygen and one is not. First, you're going to name the alkyl group that's not double bonded to the oxygen. Okay, so this is actually the one that came from the alcohol originally. Then you're going to name the part that came from the carboxylic acid, and you're going to replace ic acid with ate. Okay, so it's the easiest way to understand how to name these is to look at examples. So ethyl ethanoate looks like this. All right, so look carefully. On the right side, we see the alkyl group that does not have a double bonded oxygen. So that came from the alcohol, so that's where the ethyl is coming from. Then we see the part that came from the carboxylic acid. So that's a 2-carbon chain as well, so that's why we're going to call it ethyl ethanoate. Okay, so pause for a second and try to draw methyl ethanoate. Okay, so methyl, that's the part that came from the alcohol. So that's going to be the part that's not attached to the carbonyl group. All right, so methyl, the methyl part's on the right, and then ethanoate, that's parts on the left, and that's what came from ethanoic acid. In some ways, it's easier to answer a question like the next one, what ester would be formed from propan-1-ol and butanoic acid, because you know that the first part of the name comes from the alcohol. So I would just call this propylbutanoate. Now, you will sometimes see examples where you have two functional groups in one molecule, two of the same functional groups, okay? Now, if you were to name these, you'd have to use the prefix di, just like we did before when we had two methyl groups, right? Like 2,3-dimethylbutane. You are not going to have to name these, but you should be able to recognize them if they're named. And I think most of you would probably agree that you could draw these, okay? That's the great thing about organic nomenclature. It really does give you a pretty easy to follow roadmap. So let's just look at two examples. Ethane 1,2-diol. It's ethane with hydroxyl groups on either end, and butane dioic acid. So that's butane with two carboxyl groups, one on each end. Okay? So again, you're not going to have to be able to name these per se, but you should be able to recognize them if they're named. Okay, so this is just a summary of all the functional groups that you need to recognize and name. So again, the functional group name is written, and then the class name is written, and then the functional group is in parentheses. Okay, so make sure that you're familiar with all of these. The general formula is given, the structural formula showing the general formula, and then an example for each one. It might be good practice to go through and try to name all of these examples, since you should now know how to do that. Okay, so pause for a second, try to do that, and I'm just going to verbally go over them. Okay, so the first one would be 2-chloropropane. The next one would be ethanol. Now, I don't actually have to say ethane-1-ol, because no matter where I put the hydroxyl group, I'm automatically going to make that carbon 1. So I can just say ethanol here. The next is ethanal. And again, remember, I don't need a number for aldehydes. The next one is propanone. Now, you don't need a number for this either, because remember, for ketones, it has to be one of the carbons that's not on the end. In propane, there's only one option, and that's the middle carbon. If you said propan 2O, and I understand why, but hopefully you see that the 2 is not necessary. And then the last would be propanoic acid. All right, try these last examples, and then we will go over those. Okay, so the first one is an ester. Okay, so we have to figure out which alcohol it came from. So it came from ethanol, so we call that ethyl ethanoate. So you've actually already seen this example in the notes. And the next one is an ether, and that's ethoxyethane. Okay? If you have questions, make sure you bring them to class, and that's it.